we will be discussing some examples which are based on binding energy. Let us repeat. Binding energy. Binding energy is the energy required to separate the nucleons from the nucleus. In another way, we can define the binding energy as if Z proton and A minus Z neutrons are brought from the infinity to form the nucleus of mass MAZ, then the energy released in this process is called binding energy. So if I provide the same amount of energy to the nucleus, then the nucleons again separate out from the nucleus. So we can define the binding energy in two ways. In last example, we discussed the binding energy formula by using mass defect, and we discussed that the 1 AMU, 1 atomic mass unit, is equals to 931.5 mega electron volt. We will use them today's class. Now first example is calculate the binding energy of the nucleus 3 lithium 7. Here given that the mass of the nucleus is 7.01653 AMU and also given mass of neutron and proton. Now we know that the binding energy formula contains mass defect. So first we calculate the mass defect delta M, because in this process there are three protons and 4 neutrons, 7 minus 3. So mass defect can be calculated in this way. ZMP means 3 and MP is mass of proton, so this one is this one, and A minus Z is neutron, number of neutrons. So here number of neutrons are 4 and mass of neutron is 1.00898. So finally we get the value of delta M is 0.04216. Now to calculate the binding energy of the nucleus 3Li7, we multiply this mass defect by 931.5 MeV, then we can find the value of binding energy 39.27 MeV. This is the energy which is required to separate the nucleons, which means 3 proton and 4 neutrons, from the nucleus 3Li7. Now second example, the binding energy of 10 neon 20 isotope is 160.647 MeV. Calculate its exact mass. And given these data, and in this isotope the number of protons are 10 and number of neutrons are 20 minus 10, which is equals to 10. Now binding energy formula is this one. This is the mass of nucleons and this is exact mass of a nucleus. So the difference is called mass defect, and if we multiply this by 931.5 MeV, we get binding energy. So to calculate the exact mass, we took MAZ in this side and remaining part in another side. So ZMP plus A minus ZMN can be calculated in this way. Z is 10 and MP is mass of proton, and A minus Z is number of neutrons, which is equal to 10, and Mn is mass of neutron, and EB is 160.647. Now putting these all values in this equation, we get this one, and after calculating this one, we can find the value of exact mass, which is 19.99 AMU. Now the last example is interesting example. Calculate the binding energy required to detach, to separate first a neutron, then a proton, and in the last to separate proton and neutron in 2He4 न्यूक्लियस. यानी ये एग्जाम्पल ये कहना चाह रहा है कि जो हीलियम न्यूक्लियस है 2He4, उसमें से पहले हम एक न्यूट्रॉन को रिमूव करेंगे, फिर एक प्रोटॉन को रिमूव करेंगे और लास्ट में एक प्रोटॉन और एक न्यूट्रॉन को रिमूव करेंगे. इन सभी प्रोसेस में कितनी बाइंडिंग एनर्जी की आवश्यकता होगी इनको रिमूव करने के लिए. So mass of neutron is given. Similarly, mass of proton also given. Mass of 2He4 nucleus is this one. Mass of 2He3 is this one, and mass of 1H2 is this one. Now, first of all, we calculate the energy required to remove a neutron. So, energy given to the nucleus alpha particle nucleus to separate a neutron. So this is the remaining nucleus, and one neutron is removed from this one, and this is the alpha particle nucleus. So this is mass defect. We remove one neutron from this one and multiply it by 931.5 MeV. Putting the value of this one, which is given 2He3, this one, putting this, and mass of 2He4, this is equals to this one, 2He4, this is mass of neutron, this is 1.008665, and this is mass of 2He4, so this is this, and multiply it by 931.5. Finally we get 20.57 MeV. Now from the remaining nucleus, which is equals to 2He3, because one neutron has been removed from this one, and the remaining nucleus is now 2He3. So from this we want to remove the one proton. So one proton means one. This is the remaining nucleus after removing one proton. So mass of this one, given this is also, and mass of proton this one, and 2He3, mass of 2He3, which is also given this one, and by multiplying it by 931.5 MeV, we finally get 5.49 mega electron volt. Now the remaining nucleus is 1H2. So if finally we want to remove one proton and one neutron from this nucleus, so to remove this one we can write this as this one, mH, which is mass of proton, mass of neutron minus the exact mass of the nucleus, which is 1H2, and multiply it by 931.5. This is given. This is mass of proton or mass of hydrogen atom is equal. So this is given. This is also given, and mass of 1H2 also given, 2.01410, multiply it by 931.5. Finally we get 2.223 MeV. From these three states we must note that if we add these three 20.57, 5.49 and 2.223 MeV, we get 28.3 MeV. So if we calculate the binding energy of the nucleus of the alpha nucleus, then we get binding energy 28.3 directly. And if we remove the neutron from the alpha particle nucleus, then remove a proton, and finally we remove one proton and one neutron. In these all process, if we add the binding energy required in each process, then the sum of them also given the binding energy of the alpha particle nucleus. Thank you.